All right, so this is a quick review of some special right triangles that we have learned from geometry. We're going to need these concepts going forward for the trigonometry portion of Algebra 2. So we are going to start with a very basic formula that hopefully everybody remembers in order to find any missing side of a right triangle called the Pythagorean theorem. And what the Pythagorean theorem says, it says if you add the squares of two of the sides, that is going to equal the square of the hypotenuse, which is always the longer side of a right triangle. Both of these triangles given here are going to be right triangles, and we're going to denote that with a little box. That denotes where your right angle is, or your 90-degree angle. So the Pythagorean theorem in general says a squared plus b squared equals c squared, where a and b are two of the sides, or what are known as legs, of the right triangle, and c is always going to be the hypotenuse. So if we label these, that's c, it's the longest side, and it's always going to be opposite of the 90-degree angle. In other words, the 90-degree angle with that little box that we drew will not touch the hypotenuse. And then we've got a and b. And it really doesn't make any difference which one you call A and which one you call B in this case. So over here, C is the hypotenuse, A and B. Those are the legs of the right triangles. All right, so one of the many uses of the Pythagorean theorem is with these in particular special right triangles, it makes it easier to find the sides. And as a matter of fact, we only need to know one side if we know the relationship of these special right triangles. So the first one we're going to start with is the one on the left. This one, the angle that's made here and the angle that is made here are exactly the same. And if you guys remember, all of the angles of a triangle have to add up to 180 degrees. Well, if the right triangle portion is 90, then the other two have to add up to 90 as well, so that the whole thing adds up to 180 degrees. But if these two particular blue angles are exactly the same, then each one of them must be 45 degrees. This is what is most commonly known as a 45, 45, 90 right triangle. And the reason that this is important is because when you have two angles which are exactly the same, their opposite sides will also be the same. And again, notation from geometry, that indicates that the opposite sides are congruent. The 45-degree angle's opposite sides are congruent. So what we're going to do is, I'm going to erase this A, B, and C real quick, is we're just going to assume, and this is going to come into play when we start talking about trigonometry in the unit circle, we're going to assume to start with that one of the legs has a length of 1. Well, if that's the case, then the other leg, because it is congruent, must also have a length of 1. That it looks horrible. There, better. Okay, excuse me. So now that we know two of the sides, and those are our A and B sides, we can literally plug those into the Pythagorean theorem. So A would be 1 squared, B is 1, so that's 1 squared, equals C squared. So if I add the left side of the equation up, 1 squared is 1, another 1 squared is 1, so I get 1 plus 1, which is 2, equals C squared. In order to solve for the length of the hypotenuse, I then take the square root on both sides of this equation. The square root of c squared is c, and the square root of 2 is a decimal approximation, so we're going to leave it as an exact value of square root of 2. That's our missing side. We're going to try this one more time, and now that you guys have watched the previous videos that you guys were supposed to watch on YouTube, we're going to see what happens if we change the length of these sides. So now, instead of having those as length 1, let's try length 3. I'm going to make each one of these sides length 3. Again, they're going to be the same because this is a 45, 45, 90, so the opposite legs are going to be exactly the same. So let's see what happens now if we plug that into the Pythagorean theorem. We're going to get 3 squared plus 3 squared equals c squared. Well, let's see what we get. That's 9 plus 9 equals c squared. 9 plus 9 is 18 equals c squared. We're then going to go ahead, let me extend this page just a little bit here. We're going to go ahead and take the square root on both sides. The square root of c squared is c. The square root of 18, once again, this is not a perfect square. If it was square root of 16, it would be easy. If it was square root of 25, it would be easy. This one's not a perfect square. But from the videos that you guys watched, you should know we can actually break a perfect square out of this. We can rewrite that square root of 18 as the square root of 9 times 2. And the square root of 9, we can actually pull it out of the square root. Square root of 9 is 3, with a leftover of the square root of 2. That is our c value. So I'm going to go back up and plug that in. 3 times the square root of 2. Okay, if you kept doing this for any given number, any given value of the legs, what you would notice the pattern developing is this. I could let these legs be anything that I want to, but they have to be the same. What you should notice is the first one, and we didn't write it, but we will, is a square root of 2. The second one was 3 square root of 2. Well, if you think of the first one as being 1 square root of 2, again, that's a horrible one, sorry. And the second one is 3 square root of 2. Really all I'm doing is I'm taking the leg and I'm multiplying it by the square root of 2 to get the hypotenuse. So in the new triangle, it's really whatever the leg is times the square root of 2. Okay, so that is your important property for a 45, 45, 90. Whatever the leg is of a 45, 45, 90, the hypotenuse will always be that leg times the square root of 2. And it can be proved by using the Pythagorean theorem. Now, one other thing I'm going to talk about real quick before we move on to the other one is, what if I gave you the hypotenuse instead of giving you a leg? So I'm actually just going to sketch this at the bottom instead of messing with our finished product at the top there. So what if we had a 45, 45, 90? We'll assume that that's what this is because we're going to draw it that way. And instead, I tell you that the length of the hypotenuse is 4. Well, if I had to take the leg and multiply it by the square root of 2 to get the hypotenuse, then to get a leg, if I was given the hypotenuse, wouldn't I then just divide by the square root of 2? So if that's the case, if the hypotenuse is 4, to get one of the legs, or A or B, it's going to be the hypotenuse divided by the square root of 2. So in this case, our hypotenuse is 4, so each leg is going to be 4 divided by the square root of 2. Now, the higher level math you go, it doesn't matter if you leave it like this or if you rationalize it. we've learned how to rationalize, and it's good that you know how to do both because this will actually simplify when you do. So I'm going to show you what this would be when we rationalize. Again, you should have already seen this in the other video, but 4 divided by the square root of 2. To rationalize, you would multiply the numerator and the denominator by the square root of 2. So I would then get 4 square root of 2. Square root of 2 times the square root of 2 is the square root of 2 squared, so that just becomes 2. And then you should see that the 4 and the 2 divide to be 2 square root of 2. That's just a much simpler, little cleaner way to write the side length of the 45-45 right 90 right triangle. Okay. All right, so again, all you need is one piece of a 45-45 90 right triangle, and you can find the other 3. Same thing is going to hold true with this next one. The next one is a 30, 60, 90 right triangle. Again, all the angles, add up to 180. We once again are only going to need to know one side, and again, we can prove this using Pythagorean theorem. We're going to start off with letting A be 1. Now there is a special relationship that you have to know. If A is 1, so we're going to let A be the value 1, which is what we call the short side of the right triangle. Okay, so this is the short side. It should make sense because it is the smallest side. It is also opposite of the 30-degree angle. It's opposite of 30 degrees. See, 30 degree, when I draw the 30-degree arc, it doesn't touch the left side of this thing. That's why it's the opposite. So, whoops, one more. So the relationship is, if you know the short side, the hypotenuse is always going to be double the length of the short side, which in our case makes our C value 2. Then, using Pythagorean theorem, it's going to be a little bit different this time because this time I don't have one of the left side pieces, but we can still solve for it. So A squared is going to be 1 squared plus B squared, which we don't know, will equal C squared, which is 2 squared. So we still have to solve for B. So 1 squared is 1. 2 squared on the right side is 4. We'll subtract 1 on both sides. And we get that B squared equals 3. So taking the square root on both sides of this equation gives us that B is the square root of 3. Again, that's not a number that we know, so we could use a decimal approximation, but we're going to leave it as an exact value, square root of 3. So our what's called the long side, or the long leg, is the square root of 3. Now what you're going to find is that whatever I let the short side be, again, the hypotenuse will always be 2 times the short side. So I'm not going to actually do another Pythagorean theorem example here, but this is what you're going to find. I'm going to go ahead and erase my 1 and my 2 and my square root of 3. And what we're going to get is that whatever the short side is, I'm going to let that be x. The hypotenuse, again, is always going to be twice the short side, so we'll call that 2x. And then the long side, it's always going to be the short side times the square root of 3. And there's your relationship. Once again, all you have to be given is one side of the 30, 60, 90 right triangle, and you can find the other one. So, for example, if I was given the hypotenuse, let's say our hypotenuse was, I'm just going to fill these in real quick. Let's say our hypotenuse was 8. Well, that's double the short side. So now all I have to do to find the short side is cut it in half. So our short side would be 4. And then the long side is always the short side times the square root of 3. So this would be 4 square root of 3. Okay, not too bad if you're given the short side. Not too bad if you're given the hypotenuse. A little bit more work to do if we're given the long side, because since it's being multiplied by a square root of 3, in order to go from the long side to the short side, just like you did on the other triangle, you'd have to divide by a square root of 3. So let me do one real quick there. Erase these. So let's just say we're given, the long side is 16. Well, if I want to find the short side from the long side, I have to divide the long side by the square root of 3. So that would be 16 divided by the square root of 3. And then I could rationalize that. Do this up in the upper right-hand corner here. 16 over the square root of 3 would have to get multiplied on the top and the bottom by square root of 3 over square root of 3, which will give you 16 square root of 3 over 3. And that doesn't simplify because 3 doesn't go into 16 evenly. And then if I wanted to double that to get the long side, I just multiply the numerator by 2, and that would be 32 square root of 3 over 3. All right, so there you have your 45, 45, 90 and your 30, 60, 90 relationships. So what you really want to concentrate on is how the sides relate to each other and how you're going to get every piece of information from one to the other. All right, I think I've covered everything that we need. All this stuff is going to come back into play when we get really into the trig. When we get really into the trig portion of this stuff, you're going to have to remember all of your geometry relationships for triangles, your SOHCAHTOA, sine, cosine, and tangent, and how they relate to all these things. That's going to really help you as well. But this should take care of the special right triangles. All right.